right, we are recording. By the way, I've recorded a lot of other classes that I've done in the past, embedded systems and robotics. They're online on YouTube, and there's maybe 6,000 people who have viewed each individual lecture over the course of the last couple of years. I have right now 6,000 followers on YouTube and over 500,000 views, and I don't have any Taylor Swift videos that people can look at on my ID. So, all right, we're going to start looking at the Vahid. By the way, the homework assignment which has been given out, you'll notice that there are some questions from the book itself, which means you'd better be able to look at the book. So let's look at logic. Now, the interesting thing is you've already seen some digital logic before, right? In Engineering 1202? Didn't we do some AND gates and some OR gates and some stuff like that? So this should be pretty easy for you to follow along, at least for the beginning. So we're going to do something called combinational, well, historically I know that as combinatorial circuits, and that is where the outputs depend solely on the current conditions. So in this case we have a situation when you're not pushing a button, the output is going to be 0. When you are pushing a button, the output is going to be 1. That is a very simple combinational circuit. So, literally, B is equal to F, it looks like, right? And it might be a little bit more complex if you add something else. So, for example, remember that lamp? I think we talked about this in the first chapter. You have a motion sensor and a light sensor that will tell you if it detects motion, then A will be 1. If there's no motion, A is equal to 0. And then also it'll detect light. When there's light detected, in other words, the sun is out, B is equal to 1. When it's dark, like at night, B is equal to 0. So obviously, the time that you want the light to shine, the lamp that would be like at your doorstep or something, is if there is motion detector and it's dark, right? So let's take a look at this. If A is equal to 1, presence of somebody there, and B is equal to 0, meaning it's dark, then you light up the light. So it looks like, yeah, if this and this, then that. And then you could also have another digital system associated with if we push a button, then it doesn't light. When you do push the button, it does light, but there may be a situation where the button is not pushed and it does light, and you can't really determine the value of F based on what the input is and only what the input is. So it might have some sort of previous state that of button presses or so. And so that would be an example of something that is not a combinational circuit. So that as opposed to a sequential circuit that has memory. So keep in mind that there's going to be some combinational logic devices and some sequential logic devices. So one of the simplest one would be the switch, which is basically associated with something like a AND gate, right? So let's take a look at a switch, the basics of binary circuits, on and off. By the way, this is just a rehash of what was covered in, I believe, Engineering 1201, and I covered this in 1202, right? V equals IR. So if we just remember some of our old V equals IR, we have a battery up there that has 9 volts. And if this device here has a certain amount of resistance, and we identify our current as 4.5, so what do you think that light is? How many ohms? It's kind of up there too, right? 2. V equals IR, right? So The 9-volt potential is applied across this resistor, which in case it's a light bulb, an incandescent light bulb. 3.5 amps of current will flow. Is 3.5 amps a lot of current? The answer is yeah, that's a lot of current. Your typical mobile phone, when it's actually communicating via your regular phone call and such, is on the average about 100 milliamps, which is actually a lot of power being consumed. And that's why it gets so hot too, right? Because when you have a lot of current, you're actually heating up a lot of the components inside because the current going through has some resistance, and the resistance is what generates the heat. That's why that incandescent bulb is going to be really, really hot, because there's a lot of resistance in it. Switch is simply 3 parts: source, control, and output. And the reason I bring this up is because this is the basic concept of the electronics that we're going to be using. So in the past, we had something called a relay, which is a switch that was controlled. And in fact, how you control this particular input is what determines if the current goes through or if it does not go through. And in the past, we had relays. Then they discovered how to do something a little bit more solid state, and that was with vacuum tubes. Then there was the invention of the discrete transistor. That was done at AT&T Bell Labs. And then the integrated circuits were created to shrink these discrete transistors down even smaller. And now it gets to the point where in the year 2015, our current year, we have billions of transistors on some of our microcontrollers or microprocessors. So at least this is something you should understand about history, and that is there's a gentleman by the name of Gordon Moore, who was one of the co-founders of Intel, and he came up with an observation, is the best way to put it, which then became what we call Moore's Law. And his observation was that every component per IC would double roughly it turns out to be every 18 months. So in other words, the number of components you could put on an integrated circuit would be able to be doubled every 18 months. So over a certain course of time, you're putting more and more and more integrated circuits on the same space. And that's the reason why we're able to have a mobile phone in your pocket, like the iPhone 6, that does pretty much what computers did 20 years ago. And the current processors that we have, some of the Intel high-end i7 processors, actually have billions and billions and billions of these transistors in its own integrated circuit. That's a good question. Here is a picture of the actual silicon die, is what it's called, with this is a Pentium, so it's actually fairly old, which has all the transistors on it, and the different areas on here represents the computing part, and some other areas represent some local memory part, the memory that we call cache memory. More of that later. How many of you have actually seen up close some of the microprocessors that we have? A couple. You know what? For the next class, I'll bring in some examples. Somebody gave me an i7, and that had burned out, so I'll bring that in along with some of the really old ones that we used to use. So inside that IC, we're going to have billions and billions and billions of what we call transistors. And in this case, this is a CMOS. CMOS is the name of the technology. Gosh, all of a sudden I can't remember what CMOS stands for. Metal oxide All of a sudden, I can't remember. I hope he puts it in here or it's in the book, right?
Metal oxide semiconductor.
Metal oxide semiconductor, but I forget what C means. All right, well, I'll come up with that later. So here we have different types of metal oxide semiconductor devices, and it's really just a switch. So imagine this is what we say when we give in one type an N type of gate. When we give a logical 1 here, that means that current will flow and it conducts from the source to the drain. And when you put a logical 0, then it doesn't allow current to pass through. And in the PMOS, it works the opposite way. Basically, if you have a logic 1 that you give this gate, then no current will flow from the source to the drain. But if you give it a 0, then current will flow from the source to the drain. And that's down, 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 very much into the device. By the way, you will learn this in great detail in ECGR 3131. You'll have that lots and lots and lots of this. That's just the general operation of how that works. Now, you can imagine that gives us a lot of power. When we give it a 1, it allows current to go through. When we give it a 0, it doesn't. If you have this NMOS versus PMOS, then it works in the opposite way. A nice analogy will be to examine: are you able to get from one side of a river to the other? That being, if you have a way to, you like this, the magnet is pulling these stones together to allow you to walk through. This author does some really cute stuff in the book, right? The main thing you need to understand is that we're going to be working with building blocks associated with logic gates, because these transistors, why they're really what's represented inside physically, that's what it looks like. It's kind of hard for us to understand this. So traditionally, we've created these logic gates that allow us to represent what really happens. Representing would be, this is a gate called NOT. So if you give a 1 here, the output is going to be a 0. Or this is an OR gate. So if there's a 1 here or a 1 here, then the output will be 1. More on this a little bit later. So we're going to be worrying about these things called logic gates. But to do these logic gates, we're actually going to do some math. Oh yeah, you probably like math, right? Everybody, you love math. All right, here we go. We're going to do a different type of math called Boolean algebra, which was created by Mr. Boole hundreds of years ago. And in Boolean algebra, just like you have in your traditional algebra, x and y as variables, our Boolean algebra is going to work with our different inputs, and our operators that we use in the case of traditional algebra of plus and minus. Our operators are going to be and, ors, and nots. And actually, with an and, or, a not, you can create all the different types of logic that we're going to be using in the future. Different types of logic, meaning there may be a gate called a NAND gate, which is called a not and gate, or a NOR gate, which is a not or gate. And exclusive OR is another one. And then if you get even more complex structures, we're going to look at things called multiplexers, which is another type of digital logic building block that actually takes some of our basic ands, ors, and nots and puts them together. So we'll look at those later. So you need to understand the concept. A and B are your two inputs, and will be the output for an AND gate will be 1 only if A and B are 1. The output for an OR gate will be 1 only if A or B is 1. And the output of a NOT gate is 1 only if A is not 1. These are the simple definitions, these tables of your AND or a NOT gate. And as you can see, for example, for the OR gate, when both of these are 1, well, at least one of them is 1, so your output for the OR gate is going to be 1. And when I mean output for the gate, I also mean for the Boolean algebra aspect of this too. So in the Boolean aspect, we would say A and B, or we would say A or B for the operation of the OR, and then you would say NOT. But we also have another way to represent this. By the way, these slides are online, so you can feel free to follow along with this on your computer if you have it and you want to look and jot notes with it as you go along. Or some of you actually like to print these out and write on them. That's good as well. All right, so, there he is, George Boole, mid-1980s. I like this, to formalize human thought. So, this is, I'm sure you loved this when you were a kid, these word problems, like, I'll go to lunch if Mary goes, or John goes, and Sally does not go, because apparently I don't like Sally. So, the way you have to represent this is, all right, if F is my going to lunch, apparently this is with people in a group, right? F represents I'm going to be going to lunch. That means that I'll represent M for Mary, J for John, and S for Sally. And the one thing I have to keep in mind is that, yeah, I'll go if Mary or John goes, and at the same time that either Mary or John goes, I want to make sure that Sally does not go. By the way, the problem may be with John or Mary because, Sally may not get along with them either, right? You never know. So our Boolean formula will be M or J and not S. And the nice thing about this is that you can evaluate this as the following. And we're going to be looking at different types of ways to express this formula. So this actually is the same as F, that means I'm going to lunch. I'll go to lunch if Mary is going and Sally is not, or I will go to lunch if John goes and Sally is not going. So there are different aspects in Boolean algebra that allows you to, different laws, or I should say activities, that will allow you to transform this Boolean equation right here into something else, another one right here. So you could prove this by saying that if Sally goes to lunch and S equals to 1, then you will never go. Well, take a look at this. If Sally goes to lunch up here, remember we have an and over here. So Sally is 1, not Sally would make this a 0. So again, with the and, if anything is a 0, then you'll never have the result of that being a 1. So it's obvious that if Sally is 1, you will never go to lunch. And that makes sense, right? Because you said that up front. I will never go to lunch if Sally goes. Man, we must be the mean kids in the college, right? We're talking about not wanting to go with somebody else, all right? So one of the things to take a look at this, let me see if it's on the next page, is maybe we could build a table and kind of identify if we're going to go or not. So here, let's build a table. And this table will be simply representing our formula. And remember we said M, F is equal to M or J, correct? And not S. Remember that's what our formula was? By the way, if you guys are talking in class, you're being picked up by the microphone back there too, so you might want to watch out how much you talk. So here we're going to go M, J, and S. Now, how many different combinations are there of all of this stuff, right?
16.
All right, somebody says 16. Anybody want to say another number? 8. Anybody else want to say another number? 9? No, the answer is 8 actually. So if we have 3 different inputs, you actually will have 2 to the 3rd possibilities.
What about not S?
Well, remember, we're looking at S as just an input. The not operation on it, that's a good question. The not operation on that S is literally that, it's an operation. So we only have 3 inputs. We have M, J, and S. Now eventually we're going to want to know what F is, right? And our inputs will be, well, we could have 0, 0, 0 as my inputs, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. I'm going to split these up into little groups there. So, the question somebody had earlier was, what about not S, right? Isn't that something? Well, what we have is we have a particular operation, and that could be like an intermediate step. So we'll say not S. So we'll look at what S is our input. Here's S is 0, so not S would be 1, right? Here's it's 1, so not S would be 0. So we're just going to be the opposite of what it is represented there. And then the other thing we might want to look at is the operation of M or J. So that's 0 and that's 0 based on our tables that we saw earlier. M or J is 0. And in fact, so this one is also 0. And then this would be 1. 1 is going to be the AND of this column and that column. So in this case, that's 0 and that's 1. We AND those two together, 0. We AND these two together, 0. We AND these two together, 1, right? 1 and 1 is 1. We AND these two together, 0. We AND these two together, 1. And those together, 0. And these together, 1. And AND these together, 0. Wow, this looks like of all the possibilities, I'm only going to lunch 3 out of 8 times, right? Well, let's check this just to make sure, right? Now, we know if Sally goes, we don't want to go. So let's see, here's an S. 1, we don't go. 1, we don't go. 1, we don't go. 1, we don't go. Yeah, that checks, right? And, if we look at if either are going, well, let's see. Yeah, 2, they're both going, and Sally's not going, so that makes sense we are going. And so this is a truth table. And this is one of the tools in your toolbox for solving digital logic problems. Now we showed you Boolean algebra, and later we're going to actually show you, how to make a circuit with this, and that's another way to solve it. And then we're going to show you how to write VHDL and then run it through a tool, and that's another way to solve it. So there's all sorts of ways for you to be able to solve the operations. All right, let's go back to this. Everybody got that? By the way, this will be scanned and available online, so you can see that later. All right, back to Vahid. Yes, sir.
Where can you find these PowerPoints?
These PowerPoints are on our website.
All right.
Have you been to the website?
Yeah.
Okay. I put them out there yesterday afternoon, I believe. And this would be in the heading called Notes. Let's see if I can find that really fast. Oh, I was looking at SparkFun. Are you familiar with SparkFun? How many people have ever bought anything from SparkFun? Ooh, oh, a couple in the back. That's interesting. All right, SparkFun. Well, here, it is a place that has electronic toys. Electronic meaning, let's say I want to buy a Raspberry Pi, which is a programming board for you to be able to do all sorts of operations. Like I have my graduate students use Raspberry Pis and cameras to do facial recognition for one of their labs. So it's pretty fun. We get to use all sorts of neat hardware. All right, getting back onto the website. All right, so we are back online, and so evaluate the given Boolean equation A and B or C and D for the given values of A, B, C, and D. And you're going to have, apparently not anything working, there we go. And then we're going to have, all right, so if you have A is 1, B is 1, C is 1, and D is 1, what do you think? Is that going to be 1? Well, let's see. Is A and B will be the value of 1, correct? So 1 or, doesn't matter what C and D is, it's going to be 1, right? So the answer is yes, 1. All right, number 2. Look at this. Now we're asking for A and B or C and D. So in other words, it looks like both of these have to be 1 or both of these have to be 1. And is that the case here? No. So in that case, it's going to be equal to 0. All right, let's look at the next one. They're all 1s. Do you think our F is going to be equal to 1? Yes. Now, that's kind of tough, right? You're going to do all that stuff. So, how did I show you could do this as well? By doing a truth table, all right? So what I want you to do is to pause right now, and before you pause the tape, I'm going to give the instruction. So what I want you to do is turn to a neighbor and build this truth table. Now here's the question. How many lines is this truth table going to have? 16. Why is that? 4 inputs, 2 to the 4th lines. All right, so let's pause and work on that. All right, we're back, and we have a volunteer who showed me this, and this is a very nice truth table for this. And we'll look at the end, 0001, 0001, 0001, 1111. Hey, I like that one. Is that what you all got? And here's the question is, did you have to do the intermediate A and B, C and D? And at this point, it might be helpful to do it. If I were to ask it on a homework assignment, I would say do it. Because at the very least, then you'll be able to, thank you, sir, then you'll be able to verify that, yeah, you understand what's going on. But, keep in mind, I'm showing you a tool. A truth table. Nobody does these nowadays. Why do they not do it nowadays? because they have electronic design tools called VHDL and schematics and such that actually will do a lot of the solving of this for you. But in the same way that you learn how to do arithmetic as a kid and how to do long division, they still have you do long division, right? Okay. You need to understand the basics or the concepts of how we're doing all of this. So it's just another example. By the way, I think I now have covered pretty much everything you need to be able to do homework assignment number 2. Uh, 20 seconds. So I think you got lots of time to work on that. So now what we're going to do is we're going to have some more practice with Boolean, right? So convert the following English statement to a Boolean equation. A is 1 and B is 1. So in other words, F will be 1 if A is 1 and B is 1. That's just simply an AND. Yes, sir?
Do we use the operators?
So what you would do is you would say, well, I'm going to show another example of this later. A and B. You mean that operator called AND?
Like F equals A.
Yes. Boolean algebra will say F equals A and B. Because it's Boolean algebra. It's a mathematical equation. It's just using Boolean as opposed to regular algebra or calculus or something else. Here's another one. Either of A or B is 1. Well, that's just NOR gate, right? Or A is 1 and B is 0. Well, that would be simple. That would be A and not B. Now notice that we put the parenthesis around B because we want to associate the not with just that B. And by the way, this is like you see here, the operator AND, you need 2 inputs, right? In this, the not needs only 1 input. And in fact, you probably saw this in the one before this. This long equation, A and B was in parenthesis. So that means you do A and B as a separate unit and C and D as a separate unit. And then once you get the result from this and the result from this, then you do the OR operation. And I'm going to show a little bit later that there's an option for precedence as well. It's part of the algebra that I'll go over in a few minutes. And then A is not 0. It's it's a simple not. So it's a negative of a negative. So it's a not of a not. It's just F is equal to A. So a real world problem. A fire sprinkler system should spray water if high heat is sensed and the system is set to enabled. That would really be bad if you set it to disabled and had a fire. So nonetheless, your Boolean equation is high heat, H, and E is enabled. So basically, when H and E are 1. Because if it's enabled and there is no high heat, you definitely don't want to spray because that would ruin everything in the room, even if it did it accidentally. There you go. Simple. Now let's get a little bit more complex. Car alarm should sound if the alarm is enabled and either the car is shaken or the door is opened. So how many different inputs do we have here? 3, right? So obviously we're going to have A, which is going to be our alarm, and we'll probably have in parenthesis then, right? Something associated with shaken and open, S and O. So let's take a look. All right, so hey, there you go. A and S or D, they call it D for door. Okay, so it doesn't look like an O. Real world problems. So nice examples that you can look at later. And you could also say perhaps the door is opened, but maybe you want to say it's not closed, right? So it depends on your sensor or your input, whatever it turns out. But you really need to understand the English such that it makes sense. So, aren't you glad that we do Boolean algebra and symbols instead of this right here? Whoa, look at that. So this is the CMOS representation of an OR gate. This is the CMOS representation of an AND gate. And I could assure you, by the way, this symbol, you've seen that before, the symbol right here, stands for ground. I've done that in class before, right? And then 1 or VCC is going to be the representation of your positive voltage. And the way we work in digital logic is, let's say if our voltage we're working with electronics is 1.8 volts, that's not that unusual for brand new microcontrollers or microprocessors, then it's really a 1 is represented by a voltage close to 1.8 volts, and logic 0 is close to 0 volts. And usually the digital logic circuits will work really, really close to 0 and really, really close to 1. You won't be wandering off closer to the middle. You'll always be pegged at the top or pegged at the bottom. So if we look at, this is just the history of all this. So this just shows you the symbol that we're going to use, its truth table, and what the transistor circuit was like years ago, and how this all came about from the history. So we're going to be doing the implementation of logic circuits or logic gates. And with that, we're going to say that is the end of today's lecture, and I'll be talking with you on Tuesday. Thank you.